Hi, everybody. Welcome back to another lecture of artificial intelligence. Last week, we already started with the learning section, and I'm quickly going to repeat the section. And yeah, then we'll simply continue. So essentially, in this lecture, we will look at, in principle, at all three types of learning, like unsupervised learning, supervised learning, and reinforcement learning. And in particular, we're going to look at decision tree learning, which is a supervised learning technique, and Q learning, which is a reinforcement learning technique. And yeah, so the first part then will deal with supervised learning. Then, as I mentioned, the special case of learning decision trees, and then we're going to look into reinforcement learning. And there, the special case is Q learning. And then in the end, we are going to look at a case study where we safely learned reinforcement learning for autonomous lane changing, which is a result from our own research group. And the content is then covered by the section learning from examples. For supervised learning, actually, we have to update this. There's also some content regarding reinforcement learning, which can be found in a book, but which is presented a little bit differently compared to how we are presenting the material. Okay, so then we discussed the learning outcomes. We discussed why learning is important. I gave you a reminder about the learning agent architecture. We looked into, or we defined these three types of learning, and that's where we stopped. So today we're going to talk about supervised learning. So essentially, in supervised learning, you have a pair of input-output pairs, and the goal is to learn the function producing these input-output pairs. And this can be anything. So like a typical example would be the input of this function y equals f of x. So the x would be the pixels of the picture, and y would be whether there's a cat in the picture or not, or there's a dog in the picture, or it should output the box where you can see a ball in the picture or something like that. And but we can also discuss this from a purely mathematical point of view, where we say, okay, we have these data points, so the inputs x and the outputs f of x, or also denoted by y, and then we could try to fit certain curve here. So and we could learn what curve would be best. So of course, the easiest one is that we learn the parameters of a linear curve. And then we could think of, okay, this isn't the perfect curve. We could also say, okay, let's use a quadratic function. And then you could say, yeah, this measurement here is an outlier. Or you could say, no, this is not an outlier. We want to have a higher order polynomial and try to catch all the data points. Or you could even do something like this, which also catches all the data points. So then the first question today would be, what do you think is more realistic? The blue curve, which would be answer A, or this orange curve, which would be answer B? And you can use the tweetback link in the chat. And this should be a rather easy question. It's just a warm-up question for today.
Okay, I see around 60% chooses A.
Okay, yeah, so that is also the correct answer, because what you want to do to generalize to also new data is usually to have a simple model. And that's also called Occam's razor, choose the simplest consistent hypothesis. Of course, the straight line is not sufficient, but maybe the green or blue line is a good compromise. This orange line is very unlikely to be true. It's a very complicated model, and if you have new data, it's unlikely that this would fit the new data points. So essentially what we want to do in supervised learning is we want to find the hypothesis that explains the data the best. So given us the data, we want to have the best fitting hypothesis. And again, in the previous examples, this would be like, is it a linear, quadratic, or higher order polynomial that matches the data points? But it could also be like another function represented by a neural network, for instance, for detecting whether there's a cat in the image. And again, as we've seen when we discussed speech recognition, what is often easier is that you use Bayes' rule, and instead of trying to find a hypothesis that maximizes the data, you basically, again, still want to find the best hypothesis, but by using Bayes' rule, you can swap cause and effect, and then you just need the probability of the hypothesis plus the probability of certain data given a hypothesis. So if you have a function like y equals x squared, there is no probability. This is certain, but there are other models or other functions we want to learn which have some uncertainty, and then there is some uncertainty about the data given the hypothesis, sorry. But in many cases, this is also not uncertain. This is a probability of 1 in the correct case and 0 in all other cases. And then, of course, the probability of a simple hypothesis is higher than a complicated one in most cases, according to Occam's razor. So this is nothing you can prove, but which is just experience from the real world. Okay, so this is just an explanation of what I just said. And as I said, if you have a simple model, then this usually generalizes better. So what does it mean? So let's say you have 100 data points, and you can use, for instance, 50 of these data points to learn the model, and then you can use the other 50 to see whether these previously unknown data points would have been correctly explained or predicted by the model. And yeah, if that's the case, then this is a model that generalizes well, or there's a hypothesis that generalizes well, otherwise it's not. And what is often done in machine learning, which we will see later on in this lecture, is that you often try to split different portions of your data. So you say, if I just use 10% for training, how well can I explain the remaining 90%? Or if I use 90% of the data for training, just 10% for checking how well it generalizes, then you of course see the more data you use for training, then the better is the result. But then you can distinguish the different approaches by how fast you converge to a good solution, which is called the learning curve. So you will see this today. Good. So there are many things you can do with supervised learning. So in this lecture, we focus on learning decision trees. This is done mostly because it's a pen and paper method, so you can really figure out in detail what's going on. So that's always good to start with something simple. Also, this is good for the exercise, and also that means that this can be something that we can ask you in an exam, because as I said, this for a small data set, this is a pen and paper method. Okay, one more disclaimer. So the decision trees we're using here are different from the decision trees we've seen when we looked at lecture and on the lecture for making rational decisions in static environments. There it was that we had several consecutive decisions, and in the end, we had these decisions were then followed by random variables, and in the end we had these utility nodes. Here it's a little different. So we have a lot of attributes, and they guide us to a single decision. So this is a little different. Unfortunately, these two communities develop these things independently, and that's why the same name is used for two different types of decision trees. So what I will do now is I will skip this and come back to this slide, because I would like to first show you a decision tree, because that's easier. So this is a decision tree for deciding whether you want to wait or whether you want to enter a restaurant. So you have several attributes. So one is like how full is the restaurant? So how many patrons does it have? So is there nobody? If there's nobody, this might be strange, and you don't trust the restaurant and you don't want to eat there. because you assume if it's a good restaurant, there should be more people. If there's some, you go right into the restaurant, and if it's full, then you have to decide whether you want to wait. And if the waiting time is more than 60 minutes, you decide not to wait. If there are alternatives around, you don't know yet. And if you're hungry and the waiting time is between 10 and 30 minutes, you also don't know yet. And if you just wait at most for 10 minutes, then you will enter the restaurant. So if there's an alternative, then you want to know whether it's Friday or Saturday, because if it's a Friday or Saturday and there are alternatives, they are probably also full. If it's if it is a Friday or Saturday, you enter the restaurant because there are probably no alternatives. And if it's not, then you go for another restaurant. Also, you base your decision on whether you have a reservation or not. If you have a reservation, you enter it. If you don't have a reservation, you check whether there's a bar. If there is a bar, you will go there because you can just wait at the bar and already have a drink. If not, you won't wait. And if you're not hungry, you will go into the restaurant because you accept the waiting time. If you're hungry, you check whether there's an alternative. If there's no alternative, you go anyways into the restaurant. And if yes, you want to know whether it's raining or not. If it's raining, you don't change because you don't want to get wet. And if it's not raining, you're changing. So this is kind of an example of a decision tree. So where you see here the attributes, and in the end, you have the decision. In our case, it's just a Boolean decision whether to perform the action or not. So in this case, enter the restaurant or not enter the restaurant. And so essentially, as I said, as it's obvious from the example, we have to restrict ourselves to discrete inputs. And the decision tree reaches its decision through a sequence of tests that you have seen. An internal node represents a test of a property. Edges are annotated with the possible test values, like waiting 0 to 10 minutes or 10 to 30 minutes and so on. And each leaf node has the Boolean value which should be returned, like will you enter or will you not enter the restaurant? And this is kind of natural in many real world problems, like a how-to manual for instance, repairing things, or other decisions you have to make in life, or like some guidelines for doctors or something like that could be formulated in such decision trees. So the attributes already know. These were how many people in a restaurant, what's the wait estimate, are there alternatives, am I hungry, do I have a reservation, is there a bar in the restaurant, is it Friday or Saturday, is it raining, and what's the price? The price didn't play a role, but it is an attribute that we have in our database, and the type of restaurant. And this is then the decision tree that somebody made based on his or her preferences. And what we want to do is now we want to automatically learn this based on the given data set. So the data set, I'm just skipping this again. This is the data set. In a previous decision tree, we didn't use price, but it could be used. So you have always the attribute values, and in the end, the decision whether you will wait or not, or you will enter the restaurant or not, it's equivalent in this case. And so here we have just 12 data points. Of course, in machine learning, you often have millions of data points, but we keep this intentionally small so that we can discuss this in detail. And the nice thing about these decision trees is that they can represent any Boolean function. So this is easily explained here based on this simple example where you have this Boolean function A, X, or B. So you have this exclusive OR operation here. And of course, if A and B is false, then A, X, or B is false, and so on. If it's A is false and B is true, then the result is true, and so on. And each row in this truth table corresponds to a path in this decision tree. Like the first row is false, 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 and the end final result is false. Or here we have true, false, true, true, false, and in the final result is true. Actually, this should be green and this should be red. I'm just noting this down so we can fix this. Okay. So the thing is that if you have n attributes, then you have 10 to the power of n combinations of these attributes. So you have 10 to the n number of rows. So in the end, you have a 10 to the power of n bit number. And if you have an, let's say, p bit number, then the number of values you can represent with p bits is 2 to the power of p. So that means in the end, you have the length of the number is 2 to the power of n. And again, you have to use 2 to the power of, now 2 to the power of n. And that is the final number of possible decision trees you can create out of just n attributes. So it's double exponential. And that makes it difficult to use brute force methods, right? So you cannot just try all possible decision trees and just check which one matches best the data set. So what we will have to do is we will have to use good heuristics to build this in an efficient way. So, and we want to have very compact decision trees such that they also generalize to unseen data. Okay. Good. That's the data set. I'm not going to read this. It's just there for your reference. So as I said, it is intractable to find the smallest consistent tree because there are 2 to the power of n possible decision trees. It's double exponential. So we need efficient heuristics. And the heuristics that we're going to use is based on information theoretic entropy. Some of you might know this already. So we will use this greedy divide and conquer strategy. We will use this entropy values to decide what is the most promising attribute to choose. And then the data set is split according to that attribute. And then again, we have the same problem. We have a subset of the data now because we split the data and then we repeat everything again and again. So we will have a recursive algorithm in the end. So we will use the most important attribute first, divide the data sets into 2 data sets, and then solve this recursively. Good. So now let's move on to the next feedback question. It's an A or B question. So given is the data set. So we have 12 data points. 6 of them return in weighting, and the other 6 result in not weighting. And again, just to show you that this is true, so 12 data points, and if you want to count 1, 2, 3, 4, 5, 6 true, and the rest is false. So that's correct. And now, if we say, okay, if nobody is in the restaurant, then all of these data points who have this value would choose not to go into the restaurant. If there's some people in the restaurant, in all data points you would enter. And if it's full, then it's not decided. 2 would enter and 4 would. In 4 cases, you would not enter. And if you would choose another attribute, like what type of restaurant, whether it's French, Italian, Thai, or burger, then in each case, the number of data points where you would weight and where you would not weight is the same. So the question is, what attribute would you choose first in your decision tree? A, patrons, or B, the type?
So over 85% chooses A.
Yes, that's a good decision. Is anybody interested in writing in the chat why that's the case? And so I'm just waiting a little bit. Yes, we have a bigger information gain. That's good. And we can quickly make a decision because of that. So the thing is, if that's the first question, then if the attribute is none, we can already stop the decision. We don't have to ask any more questions. We can also already use an F here, and we can use what we use T. We used F and T, right? Yeah, and we can use a T here because in all cases it's clear that you will enter the restaurant, and only for this remaining data set we have to split the data set further by another attribute. And here, on the other hand, you don't gain any information. So no matter what type of restaurant you have, you still have as many cases where you want to stay and as many cases where you don't want to stay. Yes, so patrons is the right answer. It's just the solution. And as I said, we're going to use information theoretic entropy for that. So those of you who study engineering, so you probably know entropy from thermodynamics. And in thermodynamics, it measures the kind of, the unorder of a system. So the thing is, if you have a closed system, then the entropy will always grow. And this cannot be inverted, which has like very profound consequences for our whole universe. And that's why also it's the second law of thermodynamics, that the entropy can only increase and never decrease. Which the first law, of course, is the energy preservation. Energy cannot be lost, but it can, of course, be transformed into less valuable forms of energy, like heat, if you first had electricity or so on. And in the information theoretic sense, it's kind of similar, but it's not exactly the same. So here also we want to measure the unorder or the uncertainty. So I will first just introduce this definition, and in the second step, I'll show you an example so that you get an idea what that means. It's actually a very simple formula. So the entropy of a random variable denoted by capital V is computed as follows. So we sum over all outcomes of the random variable. Each outcome is denoted by Vk. And we multiply the probability of this outcome with the inverted probability evaluated according to the logarithmic of base 2. Logarithm of base 2. And this can be written a little bit nicer, because if you invert a function that is evaluated in a logarithm, you can instead multiply the result with -1 and get rid of this inversion. So this is just a little bit a nicer way of writing this. And now let's look at two examples. So let's say you just throw a coin, and if it's a fair coin, then it's 50% for heads and 50% for tails. And if you just insert 50% for, or 0.5 for both outcomes, then the entropy is 1. And that's the highest possible value of information theoretic entropy. That means the uncertainty is at the maximum. So you don't know what to bet on, because both are as unlikely or as likely in this case, it doesn't matter. And let's say if you have a loaded coin that you manipulated because you want to trick somebody, then in this case, in 99% of the cases, you would have heads. And if then you would bet, you would always bet on heads and make a lot of money, because you would win a lot, because you know that with a high probability, heads will be the result. And that means you have less uncertainty in the system. And if you just insert 0.99, so here you have 0.99, in the other case you have 0.01. And if you just do the math, and then you have 0.08 as a result, which is a lower number. And the unit for entropy is bit. And yeah, as I said, 1 bit is the highest, and the lowest possible is 0 bit. So that means it's absolutely certain. Okay. Somebody wrote, entropy is the myth in engineering. Okay, I wasn't aware of that, but it's certainly clear that the second law of thermodynamics is valid. Maybe there, yeah, I mean, we can we can discuss this offline. Good, but there are no other questions relating entropy, so I'll continue. So this is just a short form that we're going to introduce, because we're just interested in random Boolean variables, not in random variables with more than a Boolean outcome. So we just use Q as the probability of one of the two outcomes. And then the other outcome, of course, has the probability of 1 minus Q. And so we just need one variable here, Q, instead of having several variables. So this is just a short form of a random, like the entropy of a Boolean random variable. Okay. So if you have, let's say, p positive examples and n negative examples, then the entropy would be the number of positive examples divided by the total number of examples, and then evaluated according to this b function. That's very straightforward, so that nothing special here. And so, for instance, the restaurant training set on slide 13 has an entropy of 1 because we have as many positive as negative examples. Both have 6. And if you would compute the entropy of n divided by p plus n, that is the same because the entropy, of course, is symmetric if you have this, if you just have this Boolean random variable. Okay, so now today I'm skipping a few things because it's always easier to explain it based on an example. So let's try to quantify the information gain using entropy. So initially, the entropy is 1. So we can use b of 6/12, which is b of 0.5, which is the same as for a fair coin. And because we computed this value already, we know this is 1. And this is, of course, the same starting point for the other case where we use type as the first attribute. And then we look at the entropies of the individual subproblems. So for none, we have b of 0 or b of 1, it would be the same thing. So here I count the number of positive cases divided by the number of total cases. And the entropy for that is simply 0. There's no uncertainty. The same here. Here we compute b of 1 because I divide the number of positive cases divided by the number of total cases, which is 1. And the entropy is 0 again. And this one is a little bit more complicated. Here we compute b of 2/6. The number I don't know exactly. And in all these cases, when we use the type of restaurant, in the end, the entropy is always 0.5. Sorry, it's always 1 because we have as many positive as negative cases. Okay, so one more thing we have to consider is that this entropy, of course, is more important than this entropy. Does anybody know why the other one is more important than the left one? Maybe just type it in the chat. Yes, so there are more data points. So it's more likely that this case will happen. So the likelihood is we have 6 data points, and initially there were 12. So it's 6/12 that this will be the new entropy. And here the probability is 4/12. And this case is just 2/12. So what we are going to do now is we are going to weigh these new entropies. So the first one is 2/12 times that was b of 0 plus 4/12 times b of 1 plus 6/12 and then times b of 2/6. So it's 6/12. I don't know whether. No, yeah, 6/12 is, and 2/6 is, so everything is fine. So this is the new entropy. And we want to know how much entropy we gained. So what we're going to do is we take the original entropy and subtract the new one. So we have b of 6/12, which is the original one, minus the new entropy on average, which is weighted by the different outcomes. And that will give us the entropy, the gain in entropy. Okay, so so I'm going back to full screen, and this is written in a much nicer way here. Initial entropy minus the new entropy weighted, where we use the weights of the individual entropies, and the information gain is 0.541. And without any computation, what would be the information gain if you use type as the attribute? You can just type it in the chat. Yeah, it's 0 because it's 1 before and 1 afterwards. We don't have to do this computation because in each case it doesn't change. So that's why we can now quantify that. In fact, as you already guessed, or not guessed, but as you have already seen in the tweetback question before, that we have here much better information gain compared to type, where we have no information gain at all. So now let me go back to the general explanation. So an attribute A, as we've seen, could be number of patrons or the type of the restaurants. With D values, divides the training set into several subsets, like full, none, or some. And then for each subset, we have a certain number of positive and negative examples resulting in this entropy, where we divide the positive cases by all cases. And then we have to weigh these cases. So we weigh it by the probability that this case will happen. So this is then the size of the new data set or the subset divided by the size of the previous data set. And then we sum this over all outcomes. So this is the remainder. And then the gain is the previous entropy, which is just the number of positive cases divided by all cases minus, so of the parent node minus the remainder. So that's it actually. It's not that complicated. And what we are having now is we have 4 cases. So the first case is we can answer with yes or no. So after we found the attribute we want to use, we can answer with yes or no and are done. So here, no, yes. So for these 2 cases, we are done. This one is not yet done. So for the one where we're not yet done, we're going to apply the same trick again. So we are going to figure out what would be the next attribute that would be useful for splitting this data set. So this is the second case. We use the gain of the best gain of the remaining attributes to split it according to that best one. And then there are other possible cases. So another case could be we have no data points. So let's say you choose none, and or none is a possible value, and there's not a single data point for none. In this case, we have 2 negative, but let's say there's no data point at all. So what would you do if you don't have any data for a certain value? Okay, somebody said ignore. Yeah, the only thing is that by the definition of a decision tree, you always have to make a decision. So unfortunately, we cannot ignore it. Cancel the attribute. Also, no, we have to use the attribute to split the data set. Okay, yeah, somebody said define a default value. So that is basically what we're doing, but we're not just using true or false. What we're using is the value of the more likely. Okay, so let's say if in the parents you have more positive than negative cases, then you use just positive, and you have more negative than positive cases, you just use negative. So you use the majority of the parent essentially. So that's the third case. There are no examples left. Return a default value calculated from the plurality classification. That's a more fancy word for saying choose the case, the more probable case of the parent of all the examples that were used in constructing the node's parent. And then there's the fourth case. And the fourth case is also interesting. So let's say you have chosen none, and you have one negative and one positive, and there's no more attribute. Oh no, let's use full here, it's easier. So let's say for full you have 2 positive and 4 negative cases, but there's no remaining attribute to further split this. So that the first question is, how do you select the value? So maybe just let's discuss this first question first. So you cannot further split this. So what value are you choosing? Yeah, we can use the majority, but not of the parent, but of the current node. So in this case, we have 4 negative, 2 positive. So we would then choose, we're not entering the restaurant. And the second question is, sorry, the second question is, how can this happen? Does anybody have an idea when this can happen? Yes, somebody said noisy data, right? So let's say you have a sensor in a robot, and the value could switch because of noise, right? Sometimes it measures correctly and sometimes incorrectly. So because of things like that, you might have, for the same situation, 2 different decisions. Another thing is that the problem is inherently non-deterministic, right? So if you look at flipping a coin, in the same situation, sometimes it's heads, sometimes it's tails, so you cannot really make a decision. I mean, this is a silly example, but there are other examples where after making a decision, it's unclear what the result will be. So this is the second case. And the third case is maybe you just need another attribute. I mean, you can just come up with a new attribute, and then with that attribute, the data could be split such that it's all positive or all negative. So there's a conflict. There's either noise in the data, domain is non-deterministic, or we cannot observe an attribute that would distinguish the examples. So these are the 3 cases of the 4th case. So, and then what we do is we use the plurality classification of the remaining examples of that node. That's the algorithm. Basically, here you have the 4 cases. If it's empty, then you use the plurality value of the parents. This was the 3rd case on the previous slide. If all examples have the same classification, that was the 1st case on the previous slide, then we return the classification. If the attribute is empty, so you don't have anything else to use for splitting, then we return the plurality value of the current node. And otherwise, we're using information theoretic entropy to find the attribute with the best entropy value. So here this is denoted as the attribute which returning the best importance value or the best information gain. And then we construct a new tree which starts from where we are right now. And then for each possible value of the attribute that we chose, like patrons, for instance, we then split the data set. So we get the data points for attribute 1 for the 1st, 2nd, and 3rd attribute. And then we are creating this, then we use this smaller subset or the subset of the data set and call recursively this function. So we call decision tree learning, which is the name of the function again. And then we enter here again and go through it again. And after we went through this recursively, at the end, this branch is added to the tree. And then we build up the tree again. So you'll see this now in an example, or in the example that we're using right now. So you have the data points from x1 to x12. You have these attributes and the parent examples, and the first attribute you choose because of the best entropy is patrons. And then we see, okay, for now we iterating here these values. So for the first value, which would be a none, here none, both are false. So that means we're done, right? And then we go back into the loop and choose the next value. So the next value would be sum. So sum is the next value. And there again, everything is true. So we build the subtree, recursively enter this function again. And then we have the case, okay, all examples have the same classification. So we return this classification. Now we're going back to the previous one hierarchy level up to our previous loop. And there we have the last value, which is full. And for the case full, it's mixed, right? So when we enter recursively our function again, then we have this last case where we again have to split. And the next attribute that we use, which has the best information gain, would be hungry. Yeah, so let's look at the possible values of hungry. So yes or no. First, we look at the case no. And actually, this should be a no instead of an F here, but it's kind of the same in this case. And then all cases are clear again, everything is false. So when we enter now recursively this function, we again can return the classification. Because we're done, we go back to the previous hierarchy level, look at the second value, which is that we are hungry, and then it's unclear. And this is repeats over and over again. So we omit the next steps, we build the rest of the tree, and the remaining animation just shows, okay, this is then, we go up a hierarchy level in our recursively called decision tree learning algorithm. And then this is how we assemble everything. And in the end, we have the whole tree that we return and not just the subtree. So this is then the final result. And the nice thing is that by decision tree learning, we obtain actually a decision tree, which is even more compact than a manually obtained one. So this was the one that was obtained, let's say, by the person itself. And you see, this is a bigger tree. And so this is more compact, which is good because it will more likely generalize better to unseen data. And it's learned automatically. So that's really nice. And it's also really, I mean, you can look at decision tree learning, the Python code, the Jupyter notebook here, and you see that's really just a few lines of code which really automatically learns this decision tree. So it's like simple technique which really works well in many applications. So now let's come back to the learning curve that I already mentioned at the beginning. So what we can do now is, let's say we have 100 data points. It's more than we had just 12 in the example, but let's say you have 100 data points. And then you use just a few for training and the rest for evaluation. And then you increase the number of data points for training and reduce the one for testing the data points. So then, of course, the correct cases on the unseen data in the test fragment is improving, right? So, and of course, every algorithm would become better and better, but you can distinguish then a good from a bad algorithm by seeing how steep this curve is, right? So if you have another approach which maybe has this kind of curve, then this is worse than the other one. So of course, if your training size is almost everything, then in the end you will always be good, even if you don't have a good algorithm. But it's kind of how steep and how fast you converge to the correct result. One more thing, because there's some randomness involved. So for each size of the training set, there have been 20 runs. These have been averaged so that you get a smoother curve. Otherwise, the curve would be even more jerky. Okay, so this 100 examples split in training and test set. Already mentioned that, and as I said, for each training test ratio, 20 random splits are used and averaged, so that yeah, because it could be that some data points are better than others. And if you just take randomly 30 out of 100, in the next case, you might take 30 that are not so good. And that's why this is repeated for the same fraction of training set compared to test set. Good. So that's it about decision tree learning. So before I go into the break today, I'm using the time to announce a few of our seminars and practical courses, which are also some of which are very much related to our lecture. So this is a small commercial now, essentially, but it won't take long. So what practical courses and seminars are we offering? Of course, we also offer 2 lectures. One of them is these Germs of Computer Science, and the other one is Cyber-Physical Systems. In terms of seminars, we have, as every year, the seminar Cyber-Physical Systems, but Cyber-Physical Systems is a very general area. So we also have a lot of topics on machine learning within the seminar. And so basically what you have to do, you have to attend the preliminary lecture on 1st of February, because there all the topics will be presented. And this is the link to the preliminary lecture. And if you cannot attend it, the slides will also be available on TUM Online. Then we have a practical course on verification, controller synthesis, and design of cyber-physical systems. This is less related to the AI lecture, but here we will focus on methods to prove correctness of autonomous systems, which is also a topic in the last lecture, so lecture 14, which I will start next week, where we talk about robotics, because in robotics, for instance, if you use learning techniques and it's not safe in the end, you cannot commercialize it because it doesn't meet any safety specifications, and then you cannot sell the product. And this is like a practical course where you design software which proves that your solution is correct. Okay, again, here is the information on the date and the room, and you don't have to note this. These slides that I'm presenting to you now are also on Moodle, so you don't have to make any notes. This one is much related with the AI lecture, because this is the practical course on motion planning of autonomous vehicles, where we are also using reinforcement learning, benchmark scenario generation, safe motion verification games, and so on. And this is also, I mean, you know this because this was the first programming exercise. And there the date is the 31st of January. And we also have a practical course on reinforcement learning of for robotics, where we will do 2 things. First of all, we will train robots such that the robot moves like well in human populated environments. So if there are humans around the robot will learn how to behave to not disturb the human, and the human and robot can both fulfill the task efficiently. And the second aspect is how to assemble modular pieces of a robot such that the robot that we assemble is optimal for a given application. So we have the startup, I think I've shown this to you before, called Robo, which also works on these problems. So there the question is how to assemble these modules in a way that we obtain robots that are optimal. So this is like the example of one of these modular robots, and if we wait a little bit, you see that this robot will be deassembled and assembled again. So the good thing about this practical course is you will work on real robots. So we'll have several modules that you can work with, and also we have a real setup where we can detect humans, so that you can learn how to react well in human environments. And the other thing is, which I briefly would like to, I'm still there, right? Yeah. So which I would briefly like to mention is that also for the autonomous like motion planning practical course, we will prepare this for real vehicles. So the real vehicle will arrive around April. And however, we will have to equip this with a lot of sensors. So the sensors and the vehicle costs almost nothing. It's 50,000 euros, but the sensors coming on top of the vehicle and the computers, it costs another 600,000 euros. So this will be a very expensive vehicle. And this is a vehicle that we purchased with 10 other professorships at TUM. And we will have a huge data center with 1 petabyte of storage in the end. So this is a major project, and we will start building the software architecture for real test drive. So hopefully, but this is not certain, we can use it in a real car at the end of the semester. If not, we will have a hardware-in-the loop test case where we can already start testing it. And everybody who worked on this, of course, once the vehicle is running well, we will have then, you can then experience this in a real car, even though it will not maybe happen during the course of this semester, but maybe during the semester break. But still, we want that you have this experience that and see how well your code is working in the real car. Okay. Are there any questions regarding the practical courses? So there's one more thing. we also wanted to present to you bachelor and master thesis topics for using AI for green energy systems, because I said we have so many oil examples. So there will be a second advertisement round later in this semester where we show you this as well. Okay, good. So it seems there's no question in the chat, in the Zoom chat. So then let's have our 5-minute break and continue at 5:11. Okay, so welcome back. So now let's switch to reinforcement learning. So the nice thing about reinforcement learning, which I already mentioned, was that you can have the superhuman capabilities, because the agent will improve on its own based on a feedback from the environment. So if you have just an agent that can be simulated, or an agent in the real environment, then this agent will improve based on the state that it receives and the reward for the action that it has performed. So it performs an action and then gets some reward back, and then based on the reward changes the policy of selecting the next actions based on the state. And this way it will explore the environment and get better and better, and in the end will use more and more exploitation to use the found policy to obtain the best, like the most amount of rewards. Okay, so let's look at a simple example, like a car following example. So the agent is here, the ego vehicle, so the vehicle that we control, and there is another vehicle in front of us. And the task is to follow this vehicle and keep a safe distance. And the agent, as I said, is the ego vehicle. Everything else is the environment. For instance, this other vehicle. And there's not much else in this environment, because it's a very simple example. And then what is the state? The state in this example would be the velocity of the ego vehicle, the relative velocity, so the difference of the ego vehicle velocity and the velocity of the front vehicle, and the relative distance of these two vehicles. And the actions would be to decelerate with 1 meters per second squared, to not accelerate at all, or to accelerate. And in this case, we just have 3 actions. But reinforcement learning also works on continuous action spaces and also on continuous states. In our example, to keep things simple, we just use a discrete action space with just 3 actions. Okay, and then we need some rewards, which indicate how beneficial the last action was with respect to solving the task. So what could be good components for the reward? So here it says tweetback, but actually it's not a tweetback question. Maybe just type in the chat what things you might want to reward. So what would be good and what would be bad? Yes, don't accelerate or decelerate too much. That's good. So because that saves energy. Safety, yes. Collision would be bad. Safe distance, keeping safe distance is good. And collision is bad, right? So this is already covering most of the aspects. So we also want to keep the speed limit and then sufficient distance, and we want to check whether there was a collision or not. So if there's a collision, there will be a huge negative reward. Sufficient distance can be checked in each step, and we check whether the safe distance is met or not, and speed limit as well. Okay, so let's talk about the policy. So you know policies already from the previous lecture where we found the optimal policy for a Markov decision process. Here we don't actually want to have this optimal policy. I mean, in the end, you always want to have an optimal policy, but you can only find the optimal policy if you have the model. So we need the transition probabilities. But the strength of reinforcement learning is that you don't need a model. And because you don't need a model, we will try to learn the policy. And learning the policy means we will have to explore the state space. And that means that we will also have to make some random selections. So we will not always use the best action, but we will use, like we will not use a deterministic policy, but we will use a probabilistic policy. So in a deterministic policy that we used in the previous lecture where we had a model and could compute essentially the optimal policy, then you have a state, and given the state, you know the best action. And now what we're using is a stochastic policy where you have the state and the action given, and this will return the probability of taking this action given the state. And that, of course, the value is between 0 and 1 because it's a we will obtain the probability for a certain action A. So this is for discrete actions. If you have continuous actions, then you will have a probability distribution, of course. So for discrete actions, then these probabilities have to sum up to 1, obviously. So now exploration and exploitation, as I mentioned already, we need some exploration to randomly choose actions so that we can learn the policy, because we cannot compute it as in lecture 12 where we had a model, but now we have to learn it. But once we have a quite good learned policy, then we can use or exploit this policy more and more and use less and less random exploration and exploit really the policy to have high rewards, because if you're just exploring, the rewards are usually not good. Okay, so yeah, the trade-off is important. That's what I mentioned. So now what is the ultimate goal? Of course, the ultimate goal is to learn an optimal policy out of the set of all possible policies. So this capital P pi here is a set of policies, and we want to find a policy that maximizes our utility. So in reinforcement learning, people usually don't use the term utility, but the term value function, but it's the same thing. And as I said in lecture 12, because we had the model, we knew these probabilities, the transition probabilities, we could always choose the action maximizing the utility, and then we had either through value iteration or policy iteration, we found these optimal utilities, and if you have the optimal utilities, you also have the optimal policy. Now the difference is that we use the stochastic policy that we are learning, and that's why we don't have this max operator here, but we sum over all possible actions that this policy might choose, and then of course we weigh the rest of the utility function with the probability of that action. While as here, we chose the action based on the maximum operator and evaluated this function. That's the only difference. And because this is a small difference, we're not going to derive this formula again, because we already derived the formula for optimal policy, and now just discuss basically the main difference. So similarly, we can discuss this for the Q function. So as you remember, the Q function was basically the state action utility. So given the state and the next action, what is the sum of rewards if time goes to infinity? So for the optimal policy, we had this formula, and again, we are making the same change. Instead of using the maximum operator here, we are summing over all actions, and we use the stochastic policy here, and the rest is identical. And exactly as for the Q value for Markov models where the model was known, we can simply obtain the policy by always choosing the action that maximizes the Q value, because the Q value already tells us the sum of rewards for a given action and the state. So we just have to choose the best action. And as you've seen in lecture 12 for the utility, if you have the utilities, you have to try out all actions, and only then you can find the optimal policy for a given state. And that's the nice thing about the Q function, is you don't actually need the model. You just need the Q values, because if you want to compute the optimal policy using the utilities, you need a transition model. Should I show this in the lecture 12, or is that obvious to you? Okay, so nobody said that they need a repetition of lecture 12. Okay. So if you now look at this formula for the Q function, you see that we would replace completely the Q value of the previous step to obtain the Q value of the next step. And that can be problematic, because this can lead to a noisy learning, so that you jump a lot between different policies. And the solution is that we use the learning rate. Similar to gamma, which was this forgetting factor, so that rewards in the future are not so valuable compared to immediate rewards. We now use a similar trick, but for the learning rate now. Okay, so for some reason there's just a white page, but yeah. So the core idea is that we take the previous value, then compute the new value 1, and subtract it from the prior value. So this is the difference. And then just don't take the whole difference, but just multiply this difference with alpha, and this alpha can be chosen, let's say, to 0.1, which slows the learning down so that it's less noisy. So if alpha equals 1, this Q value and this Q value would cancel, and then the remaining formula would be identical to the previous formula, with one exception. So here we use the stochastic policy, and here we actually use optimal policy given the current Q value. So this can be done here because of the learning rate. So this works because we don't change the values a lot. If you wouldn't have this learning rate, then this wouldn't work. Exactly why we are not discussing this in detail here. So yeah,
there are some people on Tweetback that are confused, I think. So maybe you should show the definition from the last lecture of the Q value function.
Okay, so the Q value function definition of the last lecture, that is here, so that I don't have to show. What I, however, can show is how to compute the optimal policy if you don't have the Q value, but only the utilities. So let me just bring this up. Lecture 12. Yeah, some silly stuff. Okay. So it was, I think, wait, it was here, I guess. Yeah. So in the previous lecture, the policy, if you don't have the Q value, but only the utilities, was this one, where we had to find the best action given the transition model, the current reward, and the utility of the state. And of course, you need this transition model here. And if you use reinforcement learning, there are reinforcement learning approaches that make use of these transition probabilities, because if they're given, that can be beneficial. But there are other approaches that don't need that. And that's one of the main strengths of like machine learning in general, that you don't need a model. You just need data. And but you cannot do this with, you cannot find the optimal policy if you if you use so if you use the Q value, this formula is much easier. It's just this one, the one here at the bottom, and for that one you don't need a transition model. I mean, that's all I wanted to say. Okay. So this is the Q learning approach. So I mean, there are many other learning approaches. This is one of the most famous ones. And this is just shown here again, because now we are going to discuss this based on an example. Instead of this 4x3 world, we have now a 5x1 grid world, which is even smaller, so that we can follow what's going on. So actually, you are this blue robot, and you can just move left or right. And if you move left, you jump, no matter where you are, immediately to the leftmost cell. And if you move right, you always get one cell closer to the right. And if you're at the very left, you get a reward of +2. And if you get to the very right, you get a reward of +10. So of course, the reward on the right side is higher, but you need more steps to get there. So the question is, what is the best policy? And is the best policy the same for all the cells? We will figure that out. So we choose as a learning rate 0.1, and the forgetting factor gamma is 0.95. And the question is, why is, and the other one thing is, exploration is done randomly here. And the question is, why is exploration important in the learning phase? And I mentioned that already, but maybe somebody wants, I mentioned it already, so it's a silly question. So it's essentially because if you don't explore, we don't learn the best policies for all different states, but we will always probably visit similar states and don't have a strategy for all situations. And so what we're doing, we start at the leftmost spot. We go right. And at the beginning, nothing happens because we initialize the Q values with 0. And of course, there are no intermediate rewards. You only get a reward at the leftmost and rightmost cell. So nothing happens at the beginning. But then here in step 3, we go left, and then you jump to the left. So this is the special feature of this world, that when you go left, you immediately go there. And so then the previous Q value was 0. The learning rate is 0.1. And the reward that you obtain is +2 because you reach this cell with the reward. And then, you have the difference of the Q values before and after. And this, because everything is 0 now in the previous step, this has no effect. So we just have 0.1 times 2. And so the Q value that we obtain for this combination of action and state pair is 0.2. So this is the first, second, third, fourth, and fifth cell, and up is the upper values are for going right, and the lower values are for going left. Because we went left, we are updating the lower cell in the middle, because we were in the middle of this world. Okay, so then we go left again, although we are left already, which means we stay in the same cell, and that's why we also get the same reward again. Then we go right 1 time, 2 times, 3 times, 4 times. Nothing happens first because in the upper row the values are all still 0. But then we would enter the cell where you get a +10 reward. So that means that the reward here is +10 multiplied with 0.1, so that the value is 1. Again, here the temporal difference error is 0 because the values before and after were 0. Good. So we go right one more time. We get the same reward. It's exactly the same values that we insert in the formula. And the first interesting thing again happens when we go left, because then we jump left, and now we have a previous non-zero value, right? So we have the reward of 2, the immediate reward, and now we have to find the action that maximizes the Q value of the next state, and then we subtract the Q value of the current state. So there are 2 possible values, 0 and 0.2 for the next state. And so we choose the maximum value, which is 0.2, and subtract the current Q value, which is 0, because we started from here and went left. So this is still 0. So there's nothing here. So we get a new value of 0.219. Okay, then we are at the very left. And then yeah, this continues, and we always evaluate the same formula. So just as an example, we look now at the third row where we have the previous Q value is 0. That's because this is the previous Q value here. Then we have the immediate reward, which is also 0. So this is 0 here. And then we choose the best action for the next state, which in this case is +1, and subtract 0 because the Q value of the previous state and the action was 0 here. Okay, and then we go right again. And now we have a more interesting case where we have a previous Q value that is non-zero. We also have the high reward of 10, and then we can choose between the best value of the rightmost cell, which is 1 in this case, and we subtract the previous value, which was 1. So the previous value was this 1 here. Now we go into this cell and update this, and then yeah, the new Q value would then be 0.85. And this can be repeated and repeated. And after many simulations, the Q values converge, and we obtain these final values. So as you can see, for each state, the best or the higher Q value is always the upper one. So it's always better to go to the right. So then in the long run, you will have the best reward, which is kind of clear because you get this +10 reward. You just have to get there. But once you're there, you can exploit and always go right, and always get +10. While you might immediately, when you would have maybe just not an infinite time horizon, but a short time horizon, going left might be better because you go very quickly, because you jump and get quickly the +2 reward. But then when you exploit, yeah, if you would always go left there, then you always get only +2 instead of +10. So it's obvious that going right is the better strategy. So for this very simple example, we can store the Q values in a table. However, for larger problems, this is not possible anymore. So what people then do is they use neural networks to kind of represent this table in a more compact way. So you just have then the inputs here, S1, S2, S3, so the different states, and the outputs of the neural networks will be the actions. And yeah, if you have, especially if you have continuous states and actions, this is very beneficial, because then you would have to discretize the different values. So let's say for the first continuous state variable, you have maybe 100 values. For the second, you have 100. For the third, you have 100. So you have 100 to the power of n, which is the number, which would be the number of continuous state variables. And then the table would explode. And here you can use the continuous values as an input into the neural network, and then get the continuous outputs. I mean, deep reinforcement learning just means that you have a lot of intermediate layers. Most of you already know how a neural network is constructed. If you don't know, we are not discussing this in detail here because, as I said, this is part of the lecture from Stefan Günnemann, and this otherwise would duplicate the content of these lectures. So then there are, I would like to classify some of the approaches that are available. So some approaches use on-policy learning and others use off-policy learning. So on-policy learning means that you're using the same policy for exploration, then you use for updating the policy. And off policy means that the way you learn the policy and the way you're doing the exploration is disconnected. So what have we just used in the example of this 5x1 world or 1x5 world? Have you used an on policy approach or an off policy approach? Okay, so I haven't. So I'll just tell you. So this was an off policy approach because the exploration was completely random, and while we were exploring, we learned the Q values, and by learning the Q values, we learned the optimal, or like the policy. If you would have done the exploration based on the current policy or the intermediate policy that we have, then this would have been an on policy approach. So then there are different algorithm classes based on whether it's model-based or model-free. So model-based doesn't necessarily mean that you know the exact model, because if you know the model, you can just use the approach from lecture 12, but you might use a model to optimize your learning. And model-free means you don't use these probabilities at all. Actually, also this should be changed. Here we have a different notation where we have the action in the index and not as an argument. So this I should also write down. Slides 56. Okay, and in model free, we don't use models at all. We use, for instance, the Q values, and then as you've seen, you don't need the any transition probabilities to find then the optimal policy. Or we use policy optimization, where we use some explicit representation and learning of the policy directly instead of going through the Q functions. This is also something we're not going to show you in detail. It's just an overview. So here's just some popular algorithms. So I2A, called imagination augmented agents, is actually a model-based algorithm, but of course also uses a lot of model-free aspects. So it's a mix of two. But as soon as it has some model-based aspects, it usually is qualified as model-based. Deep Q networks is model-free. Secure learning policy is actually what I've just shown to you, but using a deep neural network. And then proximal policy optimization directly optimizes the policy without using Q values, which is also then a model-free approach. There are many others. This is just a short overview. What we also forgot on this slide is we haven't put this badge on that this is not relevant for the exam, so you don't have to memorize these algorithms. It's just like if you were interested in this topic and you want to know, okay, what is a typical Q learning approach, which then it would be DQ, N, or her. And if you want to know what is an approach that combines policy optimization with Q learning, then you could look into SAC, ACER, or DDPG, and so on. Also, the I2A algorithm, the model-based one, is also listed here, but there's also AlphaZero, which was used for learning Go, which was this huge success, which has had a lot of media attention. There's also this documentary about how the team in the UK developed AlphaGo. Okay, if you're interested in that. So one thing, there's also some downsides, of course, of reinforcement learning or machine learning in general. One is adversarial attacks, which is especially a problem in supervised learning. So a typical example is you put a sticker on a stop sign, and you put a specific sticker on the stop sign, which irritates the neural network. And then, for instance, it would say, oh, it's not a stop sign, but it means you have right of way. So this is really a big problem. And there are also these many examples where you have two images which look almost the same. There's just a specific noise pattern added on top of one of the pictures, and then the neural network is completely confused and would say, this is not an, it's something completely different. So there's these crazy examples that you can also find on the web. The other thing is that just testing is not sufficient. So if you would apply reinforcement learning to an autonomous vehicle, I would certainly not want to drive in it, because it doesn't guarantee any safety. And that's why we're also adding these safety layers on top of reinforcement learning in our research group, so that we can use reinforcement learning or other types of machine learning, but have safety guarantees. This is also something that, for instance, Ivan is working on, who will present you the exercise with respect to this lecture. Okay, then also the problem is random initialization. So if you put a real robot on a random place, this could immediately cause damage, because the robot might initially explore and only use bad actions, or because it is initialized in a bad way, so that catastrophic outcomes are likely. Also, like random acceleration, even if you have a good initial state, can lead to problems. Let's say, again, if you have an autonomous vehicle and it's just using exploration, and you're on a country road which is straight, and you would just try a left turn, you would probably immediately crash into a tree or another traffic participant. So this is not an option for you. So the solution is to use safe reinforcement learning. I will also show you a video on our own research regarding that. And this is also safe reinforcement learning is also part of the lecture Formal Methods for Cyber-Physical Systems, where we have these formal guarantees, and also the practical course verification, synthesis, and control of cyber-physical systems also has topics related to proving correctness of system designs. And we will also have a topic on provably verifying neural networks in a provable way in this practical course. I forgot to mention this when I presented the slides. So so now let's come to a case study. Let me just check the time, that we're running out of time. Okay. So here we wanted to train an agent to perform lane changes for an autonomous vehicle in a safe way. This is also, this is one of the papers on this topic. And so essentially, we want to do this lane changing, and the reward consists of a reward for reaching a goal that is given for reaching the goal lane. So if you don't reach the goal, but the right lane is also good. For getting closer to the goal, so that we don't have too many sparse rewards, because otherwise you just get a reward at the end, which is not good for the convergence of the learning algorithm. Of course, for crashing, you get a very negative reward, and safe distance is the same as for the vehicle following example that we discussed earlier today. And we have just 3 actions: change to the left or right, go straight, or execute a fail-safe plan. This is something additional that we need to ensure safety. How this works with the fail-safe planning will be discussed in the next lecture on robotics. And there were 16 continuous variables, like 6, we considered 6 surrounding traffic participants, like 3 in front and 3 at the back. And each had relative velocity and distance. That's why we had 12 variables. 2 variables for the goal, so the lateral and longitudinal distance with respect to the goal, the ego vehicle, and 2 variables for the ego vehicle, which were just acceleration and velocity. And we looked at 2 network types, like multi-layer perceptron network with 3 layers and 128 neurons each, and a long short-term memory network, which was actually developed at TUM, which is a very famous network type with 128 neurons. And we used 2 training modes, one vanilla approach, so the standard approach, and one with the additional safety layer. How the safety layer works, again, will be explained in the next lecture. So if you do the training, you see we had 2 safe solutions, one with the multi-layer perceptron network and one with the long short-term memory network. And you see that the two safe options are actually safe. So there were no violations of the safe distance at all, while the violations of the two other non-safe approaches accumulated, but you see that it learns, the agent learns. So later on, it doesn't increase with the same rate anymore. You also see that the safe approaches immediately provide good rewards, while the non-safe approaches take some time until they have similar rewards. You can also see that the average velocity compared, is very similar. So the average performance in the end, so because you want to move fast to your goal, is very similar. So for instance, if you say, okay, the mean velocity is 35, then in how many percent of the cases was this achieved? Then you see that these values are always similar. So this is this curve. And if you look at the goal reaching capabilities, so actually the unsafe ones had a little bit of a better goal reaching capability. However, they collided while the safe ones didn't collide at all. And in autonomous driving, this is the important thing. You rather drive a little bit slower train the system a little bit longer so that the goal reaching capability is better, because having an accident is not an option. So if in 1.3% cases of the cases you have an accident, that means we would eradicate ourselves, or only people would survive on the world which are not driving autonomously. So that's why, the safe approach is certainly better. This is a video showing the training. So we used, unfortunately, I hope you can see the video. Well, actually, I tried it and it worked. You can see it, or now it starts. Okay, so we were driving on a ring road, which has the nice feature that the road never ends. And this was trained on highway setting. And then again, we used the discrete actions and had this continuous states. And later on, you see the standard approach where the vehicle crashes a lot of times. So this is the standard approach where we crash, or then there's the second situation where we crash. And with our provably or formally correct safety layer, now the agent only drives safely, but still learns how to drive in a reasonable way. So the safety layer that we've developed is really unique. This is also something beyond our robotics startup that I would like to commercialize. And also, people who are interested in commercializing this, they should attend our practical course, because in the last startup, we recruited the startup team from the best students in the practical courses. Okay. So yeah, I know we are in overtime now, but we're almost done. So there's just a ton of things in machine learning, like classification with linear models, artificial neural networks, clustering techniques, which is an unsupervised learning technique. Support vector machines is also unsupervised, ensemble learning, and so on. And all this is covered in the machine learning lectures at our department. We have several lectures now. I mean, the basic one is from Stefan Günnemann, but we have deep learning for X, so deep learning for computer vision, deep learning for this and that. So there's a lot of things you can choose from. So now I'm summarizing the whole lecture. Learning, as we discovered at the beginning of the lecture, is needed if the environment is unknown and the designers are lazy, or if there's just no solution known. We looked at these three types of learning: unsupervised learning, reinforcement learning, and supervised learning, and looked into reinforcement learning and supervised learning in more detail. In supervised learning, essentially, you try to learn a function, but also computer vision problems can be posed as a function. So this is a very general problem setting. We've also seen that the hypotheses we should use for these functions should be as simple as possible according to Occam's razor. We have applied this to decision trees. which can represent any Boolean function. And we use this information gain heuristics to select the next attribute for splitting the data sets. And we have seen learning curves and how to split test and training sets. And also we looked into Q-learning as an example for reinforcement learning, which is not on this summary page. Okay, so thank you very much for attending the lecture today. So tomorrow is just an exercise, so we have to catch up a little bit with the exercises. Then next week we start the last topic, which is robotics, and the lecture will be rather entertaining. So we won't look into a lot of math or theory. I will show you a lot of videos showing exactly how you can apply certain concepts of AI to robotics. But before we do that, I will also show you some general concepts of robotics, because many of you don't study robotics, so maybe it's a nice final application area. Of course, we chose this because we're doing a lot of research in robotics. I mean, we also work at the chair for robotics, artificial intelligence, and embedded systems, so it makes sense. And I hope you will enjoy the last lectures, and wish you a lot of fun with the exercise tomorrow. So thanks a lot, and I wish you a nice evening. Bye.